The Bidirectional Dual-Active Bridge, or DAB, is the standard topology for high-power, isolated energy transfer. Tying this architecture to an AC grid typically requires a two-stage process, converting AC to DC and then DC back to AC. This requires a massive intermediate DC link. That intermediate link relies on heavy, bulky electrolytic capacitors. They take up significant physical space, add weight to the system, and are often the first component to fail under sustained thermal stress. This diagram shows a traditional DAB converter. We can eliminate the capacitor problem by transforming it into an AC interfacing DAB. We delete the intermediate DC link capacitor entirely and connect the secondary bridge directly to the AC output, creating a single-stage converter. This direct connection applies cycloconverter theory. Instead of rectifying the high-frequency transformer square waves into DC, it translates those waves directly into line frequency 50 or 60 Hz AC. Converting power at 100 kHz means managing switching transitions every 10 microseconds. Small timing errors lead to high-frequency switching losses, which significantly increases the heat the cooling system must dissipate. To operate efficiently at these speeds, standard switching protocols are abandoned. The system uses a hybrid modulation strategy built on back-to-back bidirectional switches. Interfacing the secondary active bridge with an AC grid introduces a strict physical requirement. The circuit has to block voltage and conduct current in both directions. Here is the hardware solution. At every secondary switch position, S5 through S8, the standard switch is replaced by two back-to-back MOSFETs. They divide labor between low-frequency line management and high-frequency chopping. The first degree of freedom in this system is the low-frequency grid state machine, operating at the line rate of 50 or 60 Hz. The microcontroller continually monitors the incoming AC grid voltage, tracking its polarity using an analog-to-digital converter or a dedicated zero-crossing interrupt. When the grid enters the positive half cycle, the protocol locks switches S5 through S8 into an always-on state. This creates a solid path for low-frequency current, bypassing body diodes, using synchronous rectification to minimize conduction losses. Offloading the line frequency synchronization to this static switch group completely eliminates high-frequency switching losses in half of the secondary devices. While those 4 switches handle the grid, the remaining 4 back-to-back partner MOSFETs execute the high-frequency modulation at 100 kHz. They are driven by extended phase shift, or EPS, modulation. EPS controls an inner phase shift governing the bridge's duty cycle and an outer phase shift setting the delay between bridges. Here, active complementary switches chop the voltage, creating a 3-level waveform across the transformer: positive, 0, and negative VAC. During positive and negative states, diagonal switches turn on, pushing power between the primary DC and secondary AC sides. Standard single-phase shunt modulation struggles here by forcing continuous power flow. During transitions, this pushes reactive back power in the wrong direction, generating excess heat. EPS prevents this back power by inserting a deliberate zero-voltage freewheeling state between the active pulses. To create this zero-voltage state, the controller turns on both top or both bottom active switches simultaneously, shorting the transformer loop. Trapping this energy stops back power and physically discharges the switch's output capacitance right before they turn on. This achieves zero-voltage switching. Because the voltage across the switch drops to 0 before the gate signal arrives, turn-on losses are eliminated. When the AC line crosses 0 and enters the negative half cycle, the roles perfectly reverse. The static switches begin high-frequency modulation, and their complementary partners lock into the always-on state. Combining the low-frequency bypass with high-frequency EPS chopping allows the converter to shape the power flow without the severe thermal penalties of hard switching. Controlling this physical power stage requires an exceptionally precise digital brain, the microcontroller. A 100 kHz loop imposes a strict mathematical reality. The processor has exactly 10 microseconds to execute its control sequence before the next cycle hits. Standard timers lack the necessary resolution. The hardware requires advanced control timers, like TIM1, or dedicated high-resolution timers found on power-focused microcontrollers. The required timer configuration is center-aligned mode. The timer counts up and down, forming a triangle wave that maps exactly to symmetrical PWM pulses. Generating these patterns natively in hardware is required to maintain precise timing for zero-voltage switching. Inside that 10 microsecond window, the microcontroller samples the grid voltage and calculates the proportional integral math. For a physical plant with a 33.6 microhenry leakage inductance and a 220 microfarad output capacitor, the PI math uses a proportional gain of 0.0332 and an integral gain of 4.71. Running this calculation yields two outputs, the new inner phase shift and the new outer phase shift. Writing these phase shifts to the timer registers using standard software interrupts introduces normal execution jitter. This delays the update, causing destructive duty cycle glitches. To solve this, the firmware uses direct memory access, or DMA, to bypass the CPU. A timer update event triggers the DMA directly, pulling calculated phase shifts from memory into the timer capture compare registers. Configured with preload enabled, they buffer incoming data, guaranteeing the new phase shifts update simultaneously on the next cycle boundary. Bypassing the CPU with DMA removes software jitter, managing the EPS calculation load without violating the strict 10 microsecond physics of the power stage. The system operates across three distinct time domains simultaneously: the 50 Hz grid, the 100 kHz switching loop, and the 10 microsecond firmware calculation. On the input side, the primary DC bridge fires steadily at 100 kHz to excite the transformer. On the right, the secondary bridge splits its duties. One switch set chops rapidly, the other remains locked. As the sine wave crosses zero, the interrupt instantly swaps their roles. Simultaneously, DMA registers calculate and apply exact phase shift offsets every 10 microseconds. By minimizing body diode conduction and achieving full zero voltage switching, the design runs cool and maximizes energy transfer. The design achieves highly efficient bidirectional AC to DC power transfer without relying on a massive, failure-prone DC link capacitor. Synchronizing this high-frequency link topology with deterministic embedded control provides the density and efficiency needed for direct AC grid integration.